Hi everyone, I am Yadgiri Rao, Assistant Professor of Chemistry, Nagarjuna Government College, and I handle the thermodynamics lesson. In the last class, we have discussed about energy is defined as trait of substance, bit difficult to define it, and basically it was expressed as a capacity to do work or to produce heat. And we know that energy is conserved means energy cannot be created or destroyed, means total energy content of the universe is constant, and the units for energy are joules, calories, ergs, quarts, tons of TNT equivalents. All those details we have learned, and also we learned that heat can be converted into work, that is partially, but work can be converted into the heat mostly in a full extent. And that was proved by Joule's mechanical equivalent of energy experiment. So, and again we learned some of the important terms of the thermodynamics, that is system, surroundings, universe, and boundary. And what is the system? System is the little part in the universe that is under our investigation for the purpose, and everything else outside this system is surroundings, and system and surroundings put together is universe. And system and surroundings may be separated by a real boundary, a surface, or sometimes it may be an imaginary surface or imaginary line. It depends on what kind of boundary. A boundary can be porous, that will be able to exchange the matter with its surroundings, and a boundary can allow the movement of heat between system and surroundings. Based on the nature of the boundary, systems are several types, that is open system, where system is in a position to transact with the surroundings in terms of matter as well as heat. Another one is closed system, where system transacts with surroundings only heat but not the matter. And one more system we have, that is isolated system, that is not in a position to have any transaction with surroundings, both with respect to matter and heat. It stays as a standalone system, no connection with the surroundings on any front, both matter and heat. So that can be expressed like this in a schematic way that we have seen in the last class. Now this is a wonderful presentation of open system, closed system, and isolated system, where open system is exchanging matter and heat with the surroundings, and closed system only heat is being exchanged but no exchange of the matter, and closed system no way transactions with surroundings. Now let's go to in a systematic way, let's categorize, let's put all these properties in a tabular form. System type, how it can transact with its surroundings. Open system, it can exchange matter with the surroundings, heat also, and there will be some work transfers between them. System can do work on surroundings, surroundings can do work on the system. The closed system, yes, it doesn't exchange matter with the surroundings, but it swaps energy with the surroundings. Work also. Isolated system, no transactions with the surroundings. Right. There are certain properties in the thermodynamics that have to be studied, because thermodynamics, as we discussed earlier, it deals with the systems at equilibrium. To express a system at equilibrium, a state of equilibrium, we need some properties. And all properties can be categorized into several classes. So we already know that properties that describe equilibrium do not change with the time, macroscopic properties. So those are pressure, volume, temperature, the individual components, moles, and masses also, both are interrelated. Now these properties are basically, from one perspective, extends they can be classified into extensive properties and intensive properties. What is the meaning of extensive properties? Extensive properties are those which are independent of quantity of the substance in the investigation. And intensive properties, the sorry, extensive properties are dependent on the quantity of the substance. Intensive properties are independent of the substance in the system. Now, excuse me. Yeah, extensive properties are quantity dependent. Examples: mass, value, number of moles, area, and force. So these we can understand very easily. And intensive properties: pressure, temperature, concentration, density, and cell potential. Take the water density. Generally, at 20 degrees, it is 1 gram per ml. You take any amount of water, its density is only 1 gram per ml. It's fixed. It doesn't change with the quantity. That means it is a quantity independent. Pressure also. Concentration is also a very interesting term. You take 1 molar concentration. You take 1 liter, its concentration is 1 molar only, and you divide that into 5 parts. Each part concentration is still 1 molar only. But why? The number of moles in those areas change, but when per unit volume, if you make it, the concentration remains same. Now, variables. What are the variables? Variables are the ones that change when the system is changing from one state to another state. And again, these variables are state variables and path variables. That is the classification of the variables. What are the state variables and what are the path variables? Let's see. A state variable is the one that only depends on initial and final states of the system. They do not depend on how those states are changing. I mean, here it doesn't depend, it doesn't care about how you have come from initial state to final state. No dependence on the history. It only where you are in the beginning, where you are at the end. No importance to the history, how you come there. Example: internal energy, enthalpy, entropy, Gibbs free energy, temperature, pressure, value, all these things. They do not depend on the path, how a state in the initial time, the system followed a path and reached a final state. That path that resulted in the change is not having any effect on these state variables or state functions. You can call them functions also, some of them, because they depend on the pressure and volume and temperature. And path variables or path functions, basically, they depend on how you come to that state. The path, for example, if you have if you have a, uh, a second, if you have a initial point here, one second, so your, this is your initial state and this is your final state. So when you go straight, let's say distance, when you travel this straight path, the distance covered is little, but if you take another route like this, the distance is certainly greater than this. Therefore, the distance traveled between the initial and final states is path dependent. So in the same way, work and heat also depends on the path, how a system at initial state reached the final state. Path dependent they are. Now, for example, a system is following a process in two stages and coming back to the original state. Again, same point. So here actually the state properties do not change because it's a cyclic process. It is coming back to the original state. But when it comes to path properties, they may not become same. There will be some changes. So okay, for example, if we have a system like this and we reached here, this is initial state and this is final state. And lift an object, therefore you need some energy. So here energy is used. Now again, displace the object from here to here. Again, energy is needed. So from here to here, so some work is done here, some work is done. But there is other path you can follow. Directly you can lift from here to here. The work done here is certainly less than this. These two put together. That means work done is path dependent. So therefore it is a path variable. Now let's go to some problems. So what is the thermodynamics? You can see option A, different forms of energy, quantitative relation between different forms of energy, energy changes in physical and chemical reactions, and all of these we discussed in the very first class. Thermodynamics is all about these three. Therefore, the answer is all the above. Now, let's go to the one more question. Limitations of thermodynamics. If you remember correctly, in the first class, we have discussed the scope of thermodynamics. And at the same time, we have discussed limitations of thermodynamics. The very first point we discussed is thermodynamics is applicable to only microscopic properties. And it deals with initial and final states of the system. And basically systems are the systems that are at equilibrium and not concerned with the speed, how speed the equilibrium is achieved. Thermodynamics do not have the ability to talk about the speeds of reactions. It can only say whether a process happens or not. If it happens, how much energy changes are involving in that process. Therefore, all these three are limitations for thermodynamics. One more question. The surface which separates system and surroundings is, what is that? A, system, surroundings, boundary, and universe. Okay, let's do all these four terms individually. System, the part which is under our direct investigation. Surroundings, everything else. And the imaginary or a real line or surface, that is separating the system and surroundings is known as a boundary. And all these things are universe, therefore answer is boundary. Next, all the other parts of the universe outside the system are known as surroundings. Okay, this is the part which we are not interested. We are interested in the system. Everything else is known as a surroundings. So we study the effect of surroundings on the system, and we also study the effects of system on the surroundings. So our perspective is only system. We are focusing on the system, and effects coming from the surroundings, effects happening on the surroundings are the consequences of system only, in terms of receiving the effect or releasing the effect to the surroundings. Next, which of the following is or are path functions? What are the path functions? We just discussed. Those depend on the path. When a system moves from one state of equilibrium to another state of equilibrium, those are work and heat. So here option A is work, option B is heat. Both are correct answer, and both A and B are given in the option C, and option D is none of these. Therefore both option A and B are correct. Option A and B are reflected in option C. Therefore our answer should be option C. Next, internal energy and enthalpy are option A state variables, B state functions, path functions, none of these. So these are actually state functions, because internal energy depends on temperature. Temperature is a variable. If you change the temperature, keeping the all other variables constant, internal energy changes. So internal energy is basically a function of temperature. If the system gains heat or work done on the system, its temperature rises. That results in the increase of internal energy. If the system does a work or it releases a heat, it releases that heat or does that work at the expense of its own energy. As a result, its internal energy. For example, let's take ourselves as an example. If we do work for 1 hour, we feel weakness. Why? Because we lost our energy. If we eat food, we feel energetic, because we are gaining the energy. So as a result, what will happen? Some kind of changes will happen. Of course, the energy we have taken, we spend in the form of work, but the energy taken is not spent in the form of work. That will certainly result in the increase in temperature. So therefore internal energy is a state function. It depends on the state only, but basically it is not directly dependent. It is first depends on the temperature. Temperature is the state dependent, and internal energy is a function of temperature. Therefore we can say that internal energy is state function. Now, so we discussed so far properties in terms of dependence on the quantity. Those are intensive properties, extensive properties, quantity dependent or extensive properties, quantity independent or intensive properties. At the same time, those properties or variables depends on the path of the system when it is moving from one state to another state are known as path variables, path functions. And if they only depend on the initial and final state, and they do not care about the history of how they are brought into that final state, those are known as a state properties or state variables. They do not care about how they are coming there. Now, how a system moves from one state to other, that's important. We are saying that some properties are state properties. They do not care about the path they followed, the system followed. But how a system moves from one state to another state, and that is actually achieved by a process. What is a process? Thermodynamic process is an operation by which a system changes from one state to another state. You are doing something on the system. As a result, system is moving from one state to another state, and what you are doing, that operation is known as a process. And there are several processes. One is isothermal process, where temperature is kept constant throughout the process. And we just discussed that internal energy is a function of temperature. Therefore, there is no change in temperature means there is no change in the internal energy. Delta U, or some books follow delta E. So the changes in internal energies are zero for isothermal processes. Adiabatic process. Before we go into the adiabatic process, for example, isothermal process, where we need to maintain same temperature throughout the process. How is that happen? Remember, we are doing a process and our aim is to do it isothermally. Suddenly there will be a chance of rise in the temperature. But how do you maintain then constant temperature? So you make an arrangement, whatever the extra heat release that results in the temperature change will dissipate into another form so that temperature maintain constant. If there is a temperature drop, try to keep that temperature at the constant level by supplying the energy from the outside. Aim is maintain the constant temperature. If there is a fall, supply heat from outside. If there is a temperature rise, do something and capture that extra energy so that temperature remains at the constant level. Now adiabatic process. What is adiabatic process? A process which brings a state of a system to another state without use of external heat. There is no flow of heat from surroundings into the system, and at the same time there is no outflow of heat from the system to surroundings. That means there is no exchange of heat between system and surroundings. So what it means? For example, in the system there is a loss in heat that results in the drop in temperature, and in the system suddenly there is a release of heat. Then what happens? That heat is not in a position to share with the surroundings. That heat remains in the system only. That brings a rise in temperature. Therefore, adiabatic in adiabatic process, temperature changes do happen. So sometimes adiabatic, let's say expansion, adiabatically without supplying any heat, system using its own energy and expanding. It is using its energy, therefore its energy drops, therefore temperature drops. So we can say that if a system expands adiabatically, it suffers cooling, it undergoes cooling. When work done on the system and mechanical equivalent of heat energy, mechanical equivalent of heat says that by using the work we can generate heat in the system. That heat is not shared with the surroundings by the system, it remains in the system. As a result, its internal energy increases, therefore temperature increases. So adiabatic compression results in heating of the system, adiabatic expansion results in the cooling of the system. So here we can say delta T is not equal to 0. As a result, delta U is E is also not equal to 0. This is adiabatic process. And there is another process, isobaric process, a process where the temperature of the system is kept constant throughout the experiment or throughout the operation of the system reaching from one state to another state. So here delta P is equal to 0. And isochoric process where or operation where achievement of final state or reaching the final state from the initial state happens keeping the volume of the system constant. That is delta V equal to 0. Here work is equal to 0. So because here there is no displacement, work is basically displacement. So here there is no change in the volume, work is 0 in the isochoric process. So these are the 4 processes how a system can be brought from one state to another state, keeping the temperature constant in the operation or avoiding the heat transactions between the system and surroundings, keeping the system at the constant pressure throughout the operation, or maintaining the constant volume of the system throughout the process. So these are the 4 processes, the thermodynamics. So now let's go to the first law of thermodynamics. What is the first law of thermodynamics? So first law of thermodynamics talks about energy. So when we are talking about energy, we have come across few words. One is heat, and another one is work, and one more word we have come across, that is internal energy. And we just learned that not just in the very beginning, in the last class, heat is a transfer of energy due to the temperature gradient, that is Q. So work is also a energy transfer other than temperature gradient. So basically in displacing the substance using the force, that is W. And here internal energy, here we are talking about internal energy, that is change in internal energy. Why? Internal energy is a virtue of the substance. Every substance has its own energy. When the heat is supplied, work is done on the system, internal energy changes. That change in internal energy is important. That is delta E. So these 3 are related in the first law of thermodynamics. The first law of thermodynamics is energy of the universe is constant. Energy can neither be created nor destroyed. That means these 3 are related, and the mathematical form of this first law of thermodynamics is delta E is equal to Q plus W. So here we have to follow some sign conventions. Why? Because heat is released by system sometimes, heat gained by the system sometimes. In the same way, work can be achieved from the system, or we can do work on the system, basically surroundings. And these heat changes and work changes can be done using the system's internal energy, and because of that its internal energy changes, that is delta E. Therefore here it is very important, always remember anything that is going into the system results in the increase of energy of the system, and anything that is coming out of the system results in the loss of energy of the system. So here if system is doing, now let's do the sign convention. The work done by the system, W is negative, then work done on the system, therefore work is positive then, because system is receiving the work, something is going into the system. Now let's talk from the heat point of view. system releasing the heat, therefore Q equal to negative. Then system is gaining the heat from the surroundings, that means it's a gain to the system, that is positive. Okay, now the final one, delta E. Forget about heat and work for some time. System is using its internal energy and doing the work or transferring the heat. So it is loss from the system's perspective, and that loss is gone maybe in the form of heat or work or in both. So in that situation, what will happen? Delta E will be negative. And sometimes you may do work on the system, or heat can be supplied to the system that results in the increase of energy of the system, therefore delta E is positive, or both heat supplied to the system and work done on the system, then there will be a greater increase in the energy of the system, therefore internal energy increases. Let's say heat is released by the system and work done on the system, and this is a problem. When heat released by the system, there is a loss of energy, and when work done on the system, there is a gain of energy. Here delta E sign depends on which is greater in the magnitude. The loss is greater than gain in the form of work, then that is going to be negative sign. If the gain is more than loss, then that is going to be positive sign. So it all depends on how much heat and work that can be flowing in or out of the system decides the sign of the delta E. So there are three variables in the first law of thermodynamics. Those are Q, W and delta E, and these three are related in the mathematical equation delta E equal to Q plus W. So this equation is useful in calculating how much energy can be used by the system to extract or to harness some kind of work from it. Or we take a system and we supply heat to that system, and that heat we try to extract in the form of the work. And here system is working as a machine or engine, a kind of intermediate that is able to transfer the heat to the work. It's an intermediate substance. Intermediacy for a transaction to make heat into the work. So wonderful thing here. So heat to work or work to heat, or both can be used to increase energy of the system or decrease energy of the system. And famous example again, automobiles, where a chemical energy when gasoline is burnt is released, that can be used to rotate the wheels, and those wheels result in the translation motion, and we cover a lot of distance. That's the work done. And how that work is done? The energy released from the combustion of the internal combustion engine. So how much energy can be extracted from a particular process by using the energy of the system or heat supplied to the system? All those things we will discuss in the next class, and the problems pertaining to this first law of thermodynamics will be covered in the next class. And thank you very much for patient listening, and any mistakes happened in my lesson, I think you accept and you will bring them to my notice, and I try myself in a systematic way not to make those mistakes in the future classes. Thank you very much.